So I'd like to get us started with our first presentation, a practical guide to seam defects in Quercus rubra by Maas. Want to come on up here and get you started.
Hi, how are you?
Good.
Hi, my name is Maas. I'm a sophomore and an ecosystem restoration and management major with a minor in forestry, ecology, and health. During the school year, I was a part of the Wisconsin Forestry Center's Red Oak Defect project, studying the impact defects have throughout a lawn. And for this presentation, I chose to give a practical guide to seam defects in Quercus rubra or northern red oak. So an outline for this presentation, we'll go over our research objectives, define what a seam is, our study design results, some acknowledgments for our project, and then open it up to questions at the end. So the objective of this project was to provide a guide for foresters and loggers to use in the field when making management and merchandising decisions on defected trees. And this was done by visually showing the extent of a defect throughout a log. Or in simpler terms, it's really hard to look at a tree with a defect on the outside and know what it's going to look like within the tree before it's cut down and milled up. And that's what our project is here to help with. And the Wisconsin Forestry Center will be publishing our photos and data as a continuation of their Forester's Photographic Guide to Defects later this year. And we chose northern red oak because it's a very economically important species to our timber industry in our Great Lakes states. So before I move on to our study design and results, we have to define what a seam is. So seams are internal fractures of the fiber, or kind of cracks within the wood. They usually occur from mechanical injury, from logging, from wind stress, frost crack, or lightning. They usually originate in the center of the tree and enlarge in both outwards towards the bark and upwards towards the tree canopy. And these cracks occur across the growth rings and continue to enlarge in throughout a tree's life. So if we take the butt of this log, for example, our tree was roughly only this large when it first got damaged. And we're able to tell this by looking at the main seam here and when it first started. So as this tree grew, our seam also grew with it. And then as these cracks enlarge, it increasingly weakens and stresses our tree, causing new cracks to form, as we see here. So it's very common for a tree with a seam to have multiple seams within it. And so now you may be wondering, well, what's a tree's defense to this? And so trees create a barrier zone, as seen as this kind of darker rounded tissue. And this barrier zone is to try and prevent our seam from spreading outward. However, the barrier zone just simply isn't strong enough, and our seams are able to break past it until it reaches the bark and splits the bark open. And once the bark is split open, a tree will try to close the bark, but it's really not able to. What we see happen often is the bark start to curl inwards and get included into the wood. So once these seams occur, a tree cannot heal this damaged tissue, and they'll be there throughout the tree's life. Here's another diagram showing that process. You see our seams originating from the center, enlarging outwards until it reaches the bark, splitting the bark open, and then we see it kind of curl inwards. So there are three types of seams: spiral, straight, and weeping. A spiral seam is as these cracks enlarge in. They also rotate up the tree. With a straight seam, the cracks just simply stay straight as they enlarge in. And with a weeping seam, it doesn't really matter how these cracks enlarge in. It's just that a bacterial infection has occurred at the site of a seam. And these trees oftentimes have like oozing liquids out of it, which is kind of cool. Moving on to our study design and methods. So our trees were selected from a site in Chatham County. We recorded the tree's height in dBH, or diameter at rest height. They were then photographed, and we gave each tree a label. They were then felled and cut into 8-foot long log sections and transported to our milling site here on campus, where we started our milling process. So for our project, we wanted to maximize our defect area. And in order to do so, we placed our seam on top of the log and centered it. That's what the red line is showing on the picture on the left. So that as we cut into this log, we can be essentially cutting right into our defect and kind of showing the maximum area of it. And then for each log, we then cut it into 1-inch increments like this, leaving the live edge mark on. And that gave us a series of boards similar to this. And then for each board, we measured our defect area and the total board area. And then we calculated the defect area as a % per total board area. And then for each board, we photographed them and then stacked them to dry. One limitation of our project was a smaller sample size. We had a goal of finishing our project within the school year, and besides seams, we also sampled 6 other defects. So we had to kind of limit the number of logs per defect we were going to mill. Moving on to our results, starting with our straight seam defect. So our first 6 boards produced were not merchantable, meaning we can't get a quality piece of lumber out of these boards, and so they were excluded from our further calculations. And that left us with our 7 to 20 inch depth boards. And we're able to see the defect as this darker line within our boards, also outlined here. And we can see our seam enlarging from the center kind of outwards as it moves towards the north. Our defect area was highest at about our 7-inch depth at about 18%, and it kind of tapers off from there. It clears up around our 16, 17-inch depth, and that's simply because our seam or the crack hadn't reached all the way to the bark on that side of the log. And here are some photos correlating with that. Now, an important thing to know about straight seams, for our project we wanted to maximize the defect area, but that's not what a sawmill would typically do. We could have rotated our log and placed our seam on the side, what the red line is showing here, so that as we mill into this log, the boards produced would be relatively free of our defect. And that's simply because we're hiding the seam by placing it on the edge. And the boards produced could still kind of enter top lumber quality. Moving on to our spiral seam defect, this tree had a really cool stump. We see, yes, we see 2, thank you. We see 2 really large seams forming, and then this really dark star heart in the center with like a bunch of cracks kind of emerging from it. And that just shows how weakened and stressed this tree was, which is very common for a spiral seam. Now with these boards, you can disregard the discoloration that's occurring. Some boards just dried faster than others before we photographed them. And then our defect is a little bit harder to see, so I did outline it in red. So with our spiral seam, our spiral defect, the cracks rotate as they enlarge it. And we're able to see that within these boards. So towards the top of our log, our seam started on the right side. And as we got towards the center of our log, the seam moves towards the center of the boards. And as we got towards the bottom of the log, the seam moved towards the left, or your right side of the boards. So our defect's moving left to right throughout these boards. So unlike a straight seam, no matter how we mill a spiral seam log, our defect will always show up. There's essentially no way we can hide a spiral seam defect. Our defect was highest at about 9-10 inch depth at about 19%, which makes sense because this tree did have that really dark star heart, and so it was really stressed in the center, and it kind of tapers off from there. And here's some photos of that. And the dark line in the third board picture kind of shows where that really dark star heart was. Moving on to our weeping seam defect, this tree did have a bacterial infection. And so it is very common for weakened and stressed trees to get diseases and infections. And with bacterial infections, they usually additionally cause discoloration and decay within our wood. And we're able to see that in our boards produced here. So our seam defect is the darker line in these boards, and the discoloration is kind of this darker wood towards the bottom. And an interesting thing to note is that we saw our seam defect from our first board produced all the way to our last. And we also saw discoloration from our first board produced to our last. So our bacterial infection was able to cause discoloration all the way throughout this log. You can also see that in our graph here. At about our 2-inch board depth, it was highest around 14%, which makes sense because that's where our bacterial infection occurred. And it kind of tapers off from there. And here's some photos correlating with that. Now, when it comes to merchandising lumber from these boards, your main goal is getting a clear cut with minimum defect. And we used a minimum size board of 3 feet and 3 inches. So a higher lumber grade would mean that your lumber is essentially free of defect, and a lower lumber grade would mean that your board has a few defects in it. So if we use these boards for example, all of these boards were our second merchandisable board from each log. With our straight and spiral seam, we're able to get 2 pretty nice clear cuts from those boards. And with our weeping seam, we're able to get 1 long but narrow clear cut. However, this does change as we move towards the center of each log. With our straight seam defect, the defect was pretty low towards the center, and we're able to get 1 really nice large clear cut. With our spiral seam, our defect was kind of diagonal in this board, which really reduces the number of clear cuts we can get, limiting us to only really 2 long but narrow. And then with our weeping seam, it gets a little tricky with discolored wood. You can still use discolored wood, but it definitely lowers your lumber quality. And that limits us to only 3 smaller clear cuts. So if we were a sawmill, and this was our straight seam log, and we're going to pretend that the main seam here is the only seam in this log, we would make a few cuts towards the top, and these boards would be relatively free of our defect. We would then turn the log over 180 and make a few cuts there, and then those boards would be relatively free of our defect. And then what would be left of this log, we would rotate then 90 degrees. We would get some few long but narrow cuts. And it's really only this portion of the log that would have the majority of our defect in it. So a good portion of this log could produce higher quality lumber. So some main takeaways. A single straight seam can have minimum impact on our sawn product. This is done by placing the seam on the edge as you mill, and the boards produced will be relatively free of our defect. With a spiral seam, it rotates within the log and reduces the number of clear cuts. And with this weeping seam, it does have a bacterial infection and is considered poor growing stock. It usually has additional discoloration and decay within the wood, and it is good forest health practices to remove those trees. Some acknowledgements for our project: the Wisconsin Sustainable Forestry Initiative for helping fund, the Stockbridge Muncie community for helping us with our tree selection and their support from their foresters, and then the Tiger Lumber Company for helping transport our logs. And a big thank you to our advisors, Dr. Warner, Dr. Demchek, Megan Espa, Paul Knoll, and Benjamin Knack. I want to thank you all for coming to my presentation and open it up to any questions you guys might have. I was that good. Yes.
With defects, do you see any increased warpage in the log? Like as it dries, do the boards turn out more warped?
I guess potentially you could have that, especially if a crack is towards the center. You could see a warp. Kind of depends how you stack it to dry though too. Yeah. Anybody else? Okay. Yes, Dr. Winchell.
What's the biggest thing you feel like you learned personally out of it?
Ooh, well, this was the first research project I've ever done. I'm only a sophomore, so I was kind of lacking some knowledge on this topic, so I really enjoyed the challenge of it, the challenge of having to research and learn about functional tree biology, which is not an easy topic. Neither is tree wound response. So luckily I had a lot of support from my advisors, and they helped me a lot through this process. So I think the main thing I got from this project was confidence to do more research down the road.
Which defects are most common in Wisconsin?
So he asked which defects are most common in Wisconsin. You know, I don't think I know that answer. Yeah. Sorry.
Well, which ones did you research?
Oh, okay. So we did seams. We also did Epicormic sprouts, which are like branching. We did tearouts, suppressed trees, butt defects. We had one with the bug in it. I think that was all of them. I might be forgetting one, but yes. Yeah.
Any sense, or what are your thoughts, or what you saw with red oak? Do you think the results are transferable to other species, or is this red oak only, do you think, here?
Well, last year the Wisconsin Forestry Center did do basically the similar design and project for hard maple, and hard maple is a bit better at responding to wounds than red oak. And I know comparing it to red maple isn't as good as responding to wounds, but it definitely can be comparable to or between species. So, yeah.
Thank you.
How many of each type of tree were you able to actually kind of get in with that?
I believe, well, we had our 3 main ones, and I believe there was a 4th, but I didn't include that one in our presentation because I believe it also had like Epicormic sprouts in it, and I just wanted to focus on seams. Yeah, so I believe it was 4. Anybody else? Yeah.
Do you think it would be necessary to do more samples in order to make sure that everything is representative?
I feel like with our samples that we did, it was efficient. There's definitely going to be variations between our defects, kind of depending on the site and what other stressors factor into these trees and like what's causing the defect. But I think it can be used, yeah, throughout other seam trees, yeah. Anybody else?
So we have our next presentation. Eric Alfredson is presenting on a practical guide to Epicormic sprouts in Orchis rubra.
So welcome everyone. My name is Eric Alfredson. I'm a senior studying forest management here at the College of Natural Resources. Over the past school year, I've had the privilege of being one of the student research assistants for the Wisconsin Forestry Center in their development of a forester's guide to defects in Orchis rubra, otherwise known as northern red oak. And this project focused on several external defects. Then we looked at how they translated as they went into the tree. And I decided to pick Epicormic sprouts for a defect to focus on for this presentation.
Did they turn that off?
Yes.
So, just a quick overview of what we're going to cover today. We have our project objectives that we had for the project, and then we're going to define an epicormic sprout. And then we'll go over some of the causes that cause epicormic sprouting, as well as the methods of our project that got us to our results. And then there are a few acknowledgments that I would like to make at the end, and then I will open it up to questions. So the objectives of our project were to analyze external defect impact on internal log quality, as well as to develop a photographic guide for northern red oak. Now, this photographic guide is going to be a follow-up publication to one that is already out there on hard maple. So what exactly is an epicormic sprout? So an epicormic sprout is a branch that is associated with a dormant bud that oftentimes originates in the first few years of a tree's life. And the picture on the right is an image of one of these dormant bud traces. So essentially this dormant bud originated around right in here, and was essentially carried along through the entire rest of the tree's life, where it eventually ended up expressing itself in the form of an epicormic sprout. So the dormant bud is not necessarily a defect until it expresses itself as an epicormic sprout, where it then forms a branch knot, which is a defect. So these are a couple examples of some epicormic sprouting. So the picture on the right is an example of some actively growing epicormic sprouts, and the picture on the left is an image of some epicormic sprouts that have since died and have been grown over by the tree. So here's a close-up of a couple overgrown epicormic sprouts. For when it comes to log grading, younger foresters such as myself can easily miss subtle defects such as these. And I know, speaking from my own experience, prior to this project, I was not even aware that these were even actually defects. So now we're going to jump into some of the causes of epicormic sprouting. So one cause of epicormic sprouting is after a disturbance, such as a thinning. So the picture on the left is an example of a fully stocked stand that has a lot of shading to the trunks of the trees. And the picture on the right is an example of a tree that has had its neighbors removed and has been released. And it now has a lot of light getting to the trunk of the tree. And because of that light, the tree is responding to that by taking advantage of it and epicormically sprouting to try and capture some of that light. So the next cause, potential cause for epicormic sprouting is tree injury. So the picture on the left is an example of an older tree tearout that was part of our red oak project. And the image on the right is essentially showing that epicormic sprouting, or that because of this defect, the tree responded by producing one of those dormant bud traces, and it may or may not have been active at one point or another in the tree's life to try and compensate for that loss of tree canopy from the tear. So the last cause for epicormic sprouting is genetics. So some trees are just simply more prone to epicormically sprouting than other trees. And that brings us to our methods. So in the fall of 2023, in September, we went to a site in Toronto County where we selected several red oak trees with various external defects for our project. And we took photos of them while they were still standing, and we collected various data such as diameter at rest height, total tree height, as well as the height of defect on the tree. We then had the trees felled and transported in October, where we then we had them transported to campus, where we then proceeded to mill them. And we essentially had the trees, we essentially wanted to mill the defect at the top. So that is what the arrow is indicating on the screen, is that we wanted to put the defect at the top, where we then proceeded to mill the trees at 1-inch increments, going deeper into the log to try and capture the extent of the defect. We then took photos of each board after milling the logs, and then we calculated the defect area by using a 1-inch by 1-inch square grid system, where we calculated total board area as well as the area of the defect within each board. And then the Wisconsin Forestry Center also has a portable dry kiln that we got to store some of our boards from the project in, and I thought it was a really cool piece of equipment that I wanted to throw in my presentation. So that brings us to our results. So meet log C4. So log C4 was a log that we selected for epicormic sprouting, and the circles on the screen are indicating locations where epicormic sprouting has occurred in this log. So as you can see, there are quite a few of them. So this is log C4 all milled up, milled at 1-inch increments going from left to right on the screen. And this is a graph of log C4. So essentially this graph is showing the impact the defect had on each individual board. And at a 4-inch depth, we had our lowest amount of impact by the defect. And then at a 9-inch depth, we had our highest at 17%. And then at a 2-inch depth and a 6-inch depth, we had were kind of some averages that I wanted to put in there to kind of give you an idea of what the average board looked like in this log. So this is a close-up at board C46. So before I explain this, I want to explain the term C46. So so C is the name that we gave the tree. 4 is the 4th 8-foot log in the tree, and 6 is the 6-inch board depth after milling the log. So essentially, from the center of the tree going outwards, you can see that a branch knot formed at one point in time, likely as a result of thinning, and that branch knot formed because there was likely a dormant bud trace that was formed and carried along at some point where it ended up turning into an epicormic sprout, leaving a branch knot. And then after a period of time, it grew, and then at some point in time, it ended up dying, which then the tree proceeded to grow over that knot and produce a few years of clean wood, where then the epicormic, where the dormant bud was carried along through that whole process, where then it ended up sprouting again into another epicormic sprout, leaving another branch knot, likely again after a disturbance like a thinning. So this is what's likely beneath those overgrown epicormic sprouts from a side view. So if you were to take these epicormic sprouts and put them at the top of the log, if you were to mill it, and if you were to mill it at like 1-inch increments to try and get some lumber out of it, this is likely what you would see from a side view. So these are this is some of our boards from log C4 compared to some common lumber grades. So there's FAS, number 1 common and number 2 common. So FAS is considered the best lumber grade and is commonly used for things like architectural moldings as well as furniture. And then number 1 common is also used for some types of furniture as well as high-end cabinetry. And then number 2 common is used for things such as lower-end cabinetry that is typically cheaper and can be found at local stores such as Menards. So essentially, to be a number 2 common board, the minimum requirements for that are 50% or 50% yield, and as well as a minimum size clear cuttings of 2 feet by 3 inches. So I highlighted the clear cuttings that you could get out of the board at the 4-inch depth, which was our best quality board according to our data. And essentially, you could mill these clear cuttings out of it. However, you would be throwing away the majority of the board. And essentially, this board did not make the 50% yield to get to a number 2 common grade. And it could be better utilized as something such as a railroad tie. So some key takeaways from this are epicormic branches highly impact the number of clear cuts that you can get in a board, as I was just saying, as well as logs with high amounts of epicormic branches are better utilized as something such as a railroad tie, where the branch knots formed by epicormic branches are not considered defects. And then lastly, they are not the most desirable trees to keep on site, because typically trees with high amounts of epicormic branches are not the most dominant trees and are typically more intermediate and typically from an economic standpoint have already reached their maximum product class that they will ever get into. Some limitations from the project were we had a small sample size because we had the goal of getting this project done within the school year. So I just circled a couple logs that were selected for epicormic sprouting, and we also had somewhat of a lack of comparable data with the hard maple defect guide. And then speaking of the hard maple defect guide, it is currently available at the Wisconsin Forestry Center for purchase, and the red oak defect guide will be coming soon later this year. Some acknowledgements that I have. So I would like to thank SFI for their financial support for the project. I would also like to thank the Stockbridge Muncie Forestry Department for supplying us with the logs for the project, as well as the University Pathways Internship Program for financially supporting me specifically, as well as the Tyreton Lumber Company for transporting the logs to campus. And I would also like to thank my advisors, Dr. Michael Demchuk, Dr. Les Werner, Megan Espy, as well as Paul Cole and Ben Kanak. And at this time, I would like to open it up to questions. Yes.
So those, Epicormic sprouts, commonly just the red oak, or could they be like in bur oak and swamp oaks and other types?
Yes, they can be found in many other species. Typically, it's going to be found in more shade-tolerant species, where they're trying to capture that light in the lower areas underneath the shaded canopy, if that makes sense.
Yeah, I just have one more question. What's going to happen to those boards? Are they just going to be like tossed for scrap? Are they going to be made like epoxy tabletops? Or?
Like the ones specifically from the project? Or?
Yeah.
Yeah, I think we ended up giving a lot of them away just to like people that were involved with the project. Yeah. Any other questions?
When I saw you were cutting open the log, I saw that there was like a bunch. It was like a big range of like percent of defect as you went into the board.
Mm-hmm.
Is there a reason why that was?
Yeah, so Epicormic branches like essentially can emerge at various points within a tree's life. So like those dormant buds that I was talking about that are often like just carried along from like the early stages of the tree's life. Essentially, they were just waiting for like favorable growing conditions. So they can appear like, say like a tree is like 40 years old and it appears for a number of years and produces a knot. And the tree might grow for like another 20 years before that dormant bud like expresses itself as an epicormic branch, creating another knot. So they can kind of vary in the sense that one board will have one of those knots in it, and the next one it'll be completely clear. If that makes sense.
Yeah, that makes sense.
Any other questions? Oh,
this is really great, Eric, and for you and everyone else that's been working on this project. So I'm thinking about how practical this is for the folks that are out there selecting logs and trying to remove these, and for the kind of after product, and trying to kind of get the best material. So I'm thinking now though about before that, when we're marking stands to try to prevent epicormic sprouting. So it's maybe outside of the scope of your project, but thinking about how can we maybe change the way that we've been marking and selecting trees to prevent the residual trees from sprouting? I don't know. Did you have any conversations about that while you're in the woods?
I know Dr. Demchuk has like talked about like intermediate trees like red maple that are like they're not like necessarily competing with the older trees, but they're like providing shade for the boles or the trunks of the trees, essentially, and that could like help.
So leaving those.
Yeah, leaving those could help prevent that.
Awesome. Thank you.
Yes.
And so with that said, is that a problem how standard operations actually have in Wisconsin for how timber's normally marked? So you were saying keeping those for bowl shading is potentially good for reducing sprouting, but are those normally kept in normal thinnings in the state?
No, they are not.
Okay, so that's possibly a problem.
I believe I saw a question back.
Yeah, so I heard the part about I understood right, the railroad ties is probably your best market for that kind of tree.
Yep.
I missed what you said the secondary markets were, because if anybody, the reason I'm asking is everybody's taking a train trip out west recently. They're not using wood for railroad ties anymore, they're actually concrete based. So if that market goes away, what did you say was the next best market?
I would say the next best market would be for something like pallets, for like number 3 common boards, which weren't specifically like on my like example sheet for those defects, but that's essentially what our boards would like grade out to be, is something like a number 3 common, which would go up to something like pallet wood or other lower grade lumber such as that.
Okay, thank you.
Yes.
So first I'd like to just compliment you on both your research project and your presentation. This was fabulous. But I'm curious, one of the things about doing a project like this is it, excuse me, it may lead you to more questions like, what are your next research questions based on what you learned here? If you were to pursue a next level project, what might that be?
Yeah, so I think there was talks about it, but they might be doing a guide on red maple to kind of compare like how, essentially like how the trees compartmentalize and how they differ between species. So the one on hard maple was probably one of the better compartmentalized species, and then northern red oak is a comparable to that, but I would say it's not as good of a compartmentalizer, but it is very, very similar to that. And then we are looking to look at red maple, which is likely not going to be as good of a compartmentalizer as these other 2 species.
Thank you.
Is that it?
We have another excellent, I'm guessing, presentation on practical analysis of tear-out-related defects in Corpus rubra due to the second trend by Hannah Kovalaske.
Hello everyone, thank you for coming today. As you said, my name is Hannah Kovalaske, and since you guys have all been here for Eric's, this is going to be a little bit of a repeat of some information, but there will be some new stuff in there too. So I'll be presenting a practical analysis of tear-out-related defect in Corpus rubra, or northern red oak. We'll be moving through our research objectives, some basic biology, our methods, results, implications of these results, acknowledgements, and then at the end we'll have some practical questions. So moving into our research objectives, we had hoped to analyze how a defect moves through a log with this project. We had also wanted to create a guide for foresters and loggers in the field as they make decisions on whether to leave trees standing to maximize volume or to cut trees down to minimize decay impacts. So moving into some branch attachments, there are essentially 2 different ways that trees form branch attachments. Lateral branches, which look like this, and codominant stems, which look like this. Behind the scenes, those attachments look more like this. Lateral branches will create a layering effect of branch and trunk tissue. This occurs over several growth seasons and creates a very strong point of attachment. This layering effect is not present in codominant stems. Because codominant stems do not have this layering effect, there is much weaker tissue. If a tear-out were to occur on these trees due to a windstorm or ice storm or other such occurrence, it could potentially open the entire trunk up to decay. Codominant stems also typically have some measure of included bark, or bark that forms within the trunk of the tree. Lower amounts of included bark, as seen on this end, will be stronger points of attachment, but the more included bark you have, the weaker your attachment typically is. When wounded, trees will do 3 things. They will first contain this rate of decay. They will do this by using 3 walls of defense, which are present at the time of wounding. Wall 1 stops this rate of decay up and down the tree. This is the weakest wall. Wall 2, the second weakest wall, prevents the spread of decay further into the tree. Wall 3, the strongest wall, prevents the radial spread of decay. After trees have contained the wounding, they will separate tissue that is present at the time of wounding from new tissue. They will do this by forming wall 4. Eventually, with this wall, they will close the wound. Moving into our methods, in September of 2023, trees were selected from a site in Channel County. While in the field, we measured tree height, defect height, and diameter of breast height. Trees were also given a numerical code for organizational purposes. Trees were later felled by Stockbridge-Muncie Forestry staff and cut into 8-foot-long logs. Stockbridge-Muncie also transported these logs to the UWSP wood lab. Once at the wood lab, we milled these logs into 1-inch thick boards. Logs were placed defect up on the mill to maximize decay impact. Typically, you would not mill logs like this, although that does depend on your defect. With certain defects, you can arrange the log in a different way so that the defect is kind of hidden. However, because we wanted to see how that defect kind of affected the whole log, we placed them with the defect upward. Boards were also labeled as well. After milling, boards were photographed and data was collected using a 1-inch square grid. This grid was placed on top of the board and we counted defect area by hand. This data was then put into an Excel spreadsheet. We then stacked boards and kiln dried them. Because we had wanted to get this project done within the school year, we ran into some scheduling issues just given field sites and transporting. Because we sampled multiple defects for this project, we also had smaller sampling sizes. Moving into our results, this is a codominant tree. This tree had a 20-inch diameter and was 84 feet tall. In the field, we have written this tree in as a tear-out because this point of attachment is so weak that eventually it probably would have torn out. When milled, this is what the first half of the tree looked like. You can see the presence of included bark on several of these boards, which again supports the theory that this tree had a very weak attachment that likely would have torn out. However, this decay is minimized when we look at the back half of the board. As you can see, it looks a lot cleaner and nicer than the front half. We saw our highest defect area to board area at an 8-inch depth. As you can see, the defect affects the whole board all the way through the center. However, this drops off at a 12-inch depth. The first half of the board is still high, as you can see with this example at 5-inch depth. The little blip at the 16-inch depth is likely unrelated. In total, 11.37% of the area was affected by defect. Eventually, a tree with those codominant stems might look something like this. This is a tear-out, and this tree had an 18-inch diameter and was 79 feet tall. You can see by the advanced wound wood formed here that this is an older wound. This tree also had 2 defects lower in it, including a seam and another codominant stem. When milled, this is what this tree looked like. You can see the advanced decay present on the first half of the boards. Our highest defect area to board area was at a 3-inch depth, which you can see because this board was so small, obviously that ratio is going to be a bit higher. Defect impact began to clear up at an 8-inch depth, although the lower half of the board does still have defect present. This is what the defect area looked like at a 5-inch depth. In total, 14.3% of the area was affected. Northern red oak is a moderately good compartmentalizer. However, compared to a tree such as sugar maple, you can see that it's losing any competitions you might put it in. One thing to note about this tear-out is that this is an older injury, so eventually a tear-out like this on the northern red oak might look something like this, except it would be more pronounced. Moving on to some merchandising impacts. When merchandising, you want to attain a minimum size clear cut for each grade you are trying to attain. You also want to minimize defect. Boards with more defect will be lower in value. If we look at some examples from the front half of the trees, we can see that even though there is defect present, there are still some areas where we can get merchandisable lumber, although these areas are not very high. On the 5-inch depth, we have no opportunity for clear cuts. However, on the 7-inch depth, we can get a few narrow clear cuts out of there, but that's not the most valuable lumber. If we look at the codominant examples, we can see that on the 7-inch depth, because the defect mainly affects the top half of the board, we do have quite a sizable chunk, but it's not quite as long as we might like it to be. On the 10-inch depth, we can see that any cuts we might get are pretty narrow, which is restrictive of the width. However, if we look at the back half of these boards, we can see that our clear cut potential is maximized. On the 9-inch depth, we can see that the upper half of the board, we can get several clear cuts out of it. On the 11-inch depth, we can see the same thing. You might say that the bottom half of the 11-inch depth also looks good, and you could get a few small cuts out of that, but those nuts will disqualify that from a higher grade. Looking at our codominant examples, we can see that our clear cuts are greatly expanded, and we have a lot more potential there to get merchandisable lumber out of. Although tearouts and codominant stems do have potential to be pretty damaging defects, we can still get quite a bit of merchandisable volume out of these logs. The older a tearout injury is, the more likely decay is to be severe, meaning that you want to harvest trees with tearout injuries relatively soon after they've been injured. This research will be published by the Wisconsin Forestry Center this fall in the Forester's Photographic Guide to Defects in Northern Red Oak. This will be a follow-up to the Photographic Guide in Hard Maple, which was published last year. We'd like to thank the Sustainable Forestry Initiative for their funding of this project, as well as the Stockbridge-Muncie Forestry Department and Tigerton Lumber for their support. I'd also like to thank project advisors Dr. Les Werner, Dr. Mike Demchuk, Megan Espy, Paul Cole, and Ben Knack for their support. Any questions? Yeah.
I recognize this is beyond the breadth of what you were researching here, but if there are codominant stems in an easement, like in the electric utility easement or by a recreation area, would you recommend that those trees need to be removed? Is there significant risk?
That is a great question, and I would say that generally, because codominant stems are weaker points of attachments, it would be good to remove those. Any big storms that come through, you have a much higher risk of just a limb falling, which is never good. You could do like a tree risk assessment. I know that's common in urban forestry practices to look at whether that's something that needs to be immediately removed or whether it's a concern that you'll want to monitor and see if it starts splitting or gets worse as time goes on. That's a good question. Yes?
Looking at the picture that were kind of in common across the talks here, I think I saw you, Eric, and Alice in a lot of the field pictures. So we had defects on seams, we've had defects with Epicormic branching, we have defects on tearouts. Looking at the trees from your perspective, which ones can you spot right away? Which ones do you really need to focus on?
Yeah, that's a great question. So I'd say that is definitely something that you get better at with experience. I did not have very much field experience, so someone like me might not have immediately recognized Epicormic sprouts as a defect, whereas something like a tearout is usually pretty obvious. A non-forester might not see that as like, how much merchandisable lumber can I get out of this? They might see that more as like, there's a branch missing. But that defect is a lot more obvious than some of the ones like Epicormic sprouting or suppressed trees. That's another defect that we studied that was not covered in a presentation. But I would say that one takes a trained eye to see. So it kind of depends on your level of experience.
Thank you.
Anyone else? Yeah.
What would be the big takeaway you would want to give for a, if you had a forester in the audience here and you have many, what would be the main takeaway you would want them to get out of this?
I would say the main takeaway would be that because tearouts can cause such decay throughout the trunk of the tree, it's important when you have these injuries to harvest them as soon as you can get out there. So that way you can save as much of the merchandisable lumber as you can. The older the injury is, the more likely that decay is to be spread throughout the tree. Anyone else? Yeah.
What if I'm a wildlife biologist and I'm asking his question?
I would say as long as you don't have anything that you'd be worried about getting hit by a fallen branch or anything like that. If it's in the middle of the woods and there's nothing that is going to hurt if the limb falls out or if you want the snag to stay out there, then, as long as it meets your management goals. Anyone else? Yeah.
What's the biggest thing you personally learned out of doing this project?
Yeah, so I did not have very much experience, especially with the merchandising. I had never thought about that, like where wood products come from and why some of them are more expensive or some of them are more cheap. So I would say that getting to get that background in the merchandising side was really interesting. I also really enjoyed getting to kind of go through every step of doing a research project, from going out in the field and selecting your samples, and then going through other research that's been done and coming up with a presentation. So that's all been really fun to experience and do firsthand. So, yeah. Anything else? All right. Thank you.